part 3 of our sequences and series. Now going on to our geometric series. This might be a little bit familiar. This is referred to also as the constant ratio. Okay, in a similar manner to how we did the arithmetic, we have series, which are the additions, right, when we add them, and then we also have sequences, and that is when they're listed, separated by a semicolon. So we're just going to go into what the formulas are. For the sequence, it is Tn is equal to A times by R to the power of n minus 1. Notice the separation here. These are different bases. The n minus 1 is an exponent to base R, okay? A, as always, the first term, but here R is the ratio, the constant ratio, okay? Remember how we said that the difference was obtained in arithmetic? We said D is equal to T2 less T1. So here, to establish the ratio, not the difference. The ratio is by taking term 2 and dividing it by the term before, okay? And it works for all consecutive terms. You can take term 3 and divide it by term 2, because how we got from the one term to the next term, it's by that same multiplicative factor, okay? So it looks like A for our first term. The next one is A times that ratio value. The next one is A times that ratio twice, so it's R squared. And we carry on with that process, A by R to the power of 3. Now for the series, the formula looks as follows. It's Sn is equal to, in our numerator, it's A times R to the n minus 1. And all of that divided by R minus 1. So A first term, R ratio. Notice the similarity in our numerator and denominator. They simply differ, obviously, by that multiplicative A first term, and then as well as that exponent n. Now, with this series in a geometric specifically, because of this factor, right, it enlarges numbers and it reduces numbers, okay, depending on what R is, of course. Sometimes you can get a concrete answer like we did with the arithmetic one, right, concrete. That's when you'll use this one. If you have a ratio value, which is less than positive 1, but greater than negative 1. So it's somewhere in between. It's going to cause your geometric sequence to fluctuate like this. Shoop, 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 almost until it reaches like a flat line, like equilibrium, to the point that these positive and negatives are going to become obsolete. So this is a concept called the sum to infinity, because it's going to have this continuation for an endless amount. So it's kind of taking into account what all of these terms would be, unlike this, which has a concrete term number, and then figuring out what would the sum of these infinite terms add up to. Okay, so sum to infinity is equal to A over 1 minus R. First term, ratio value. So depending on what you're working with, you're going to use one of these two, okay? Determine the geometric sequence of which the first term is -3 and the fifth term is -243. So we have term 1, also known as A, that's -3. And then we have term 5 as -243. So remember, we need to know what is our A value as well as our R value. So I have A, now I need to try to figure out R. So I'm going to take this term 5 and apply it to my ratio formula, my geometric sequence formula. So Tn is equal to A times R to the power of n minus 1. Now, my A value, it's constant throughout this because it's always going to be the first term here. So that's -3. My ratio value, I don't know. But I know this. This is an input. 5 is an input and this is an output. So where I see n, I'm going to plug in which is 5. So that is going to be the, excuse this, 5 minus 1. And the output to this is the minus 243. And you can clearly see that r is the only thing we don't know the value to. So we're going to solve that. So I'm going to divide it on both sides to eliminate that. Minus 243 divided by negative 3 is 81. And that leaves me with r raised to the power of 4. So I need to figure out what can I raise to the power of 4 in order to find this value. So one way we can do this is to do prime bases. So I know if I re-express 3 raised to the power of 4 is 81. So that means r is equal to r to the power of 4 as well. Using this deduction, because the exponents are the same, the bases would be the same. So the ratio value is 3. So to now figure out the general sequence, we put it in the structure. So Tn is equal to A, that's minus 3. R is 3 raised to the power of n minus 1. Calculate minus 2 plus 10 plus negative 50 to 7 terms. Now, if this is all that they give you in the question, you need to establish if this is going to be an arithmetic type of series or a geometric series. Series because we're plussing the terms together, okay? Now, looking between term 1 and term 2, you can see a multiplicative factor, right? So to go from this one to this one, because we're doing the summation, we are going to use the SN formula. Sn for a geometric series is A multiplied by r raised to the n minus 1 all over r minus 1. The value of A being a first term, negative 2. The ratio value, we need to obtain that. So remember, to get the ratio value, you can take term 2 and divide it by term 1. Is 10 divided by negative 2, which is negative 5. And that's consistent to go from 10 to negative 50 as well. And then our n value, they tell us they want it to 7 terms. So now let's just plug all of that in. So the sum to 7 terms is equal to A, negative 2, multiplied by our ratio factor, which is negative 5. I'm going to put that in a bracket because I'm raising it to the power of n. Okay. Raised to the 7 minus 1 over our ratio, which is minus 5 minus 1. That's negative 26,042 is to 7. Determine a value that is the sum to the series 32 plus negative 16 plus 8 plus the rest of the terms all the way up till 1/8. Let's start to establish what type of series this is. I can see there's clearly no constant difference. So let's possibly evaluate a constant ratio. Ratio is equal to term 2 divided by term 1. Term 2 is negative 16. And term 1 is 32. All right, simplifying that gives us negative 1 over 2. So this is what we call a converging series. Converging series, when things converge, it means it comes together. So you can see it's almost hitting this phase of equilibrium. So sum to infinity. So we're going to look at that now. Your ratio value is less than positive 1, but greater than negative 1, then it's going to follow this trajectory of a converging series. So our r value is equal to negative 1 over 2. Now, that means our r value is less than 1, but it's greater than negative 1. So to write our formula, the sum to infinity is a over 1 minus r. So a is our first term, and that's 32. 1 minus r. R is our ratio value, minus 1 over 2. It is 64 over 3, or if you want to write that as a decimal, you could say 21.33, rounding off to 2 decimal places. So that is the answer to the sum to infinity. Drop us a like and subscribe, and we'll see you in the next episode.